Okay, so there are a couple of nice articles that just appeared in Science in, just a couple of weeks ago, January 2025. These are about whether we can sequester carbon into building materials and what is the potential in terms of carbon capture. Building materials are being used extensively, and with economies like India and China growing, infrastructure, buildings, residences, commercial, etc., are expected to continue to grow, and even the older, richer countries often tear down older buildings and rebuild and so on. So this says building materials could store more than 16 billion tons of CO2 annually. Okay, we're emitting somewhere around 30 to 40 billion tons right now per year. Of course, greenhouse gas equivalent will take us from 40 to 50 billion tons, but that could be a significant fraction as long as buildings continue. Achieving net zero greenhouse gas emissions likely entails not only lowering the emissions but also deploying carbon dioxide removal technologies. We already discussed this in various contexts. We explored the annual potential to store CO2 in building materials. We found that fully replacing conventional building materials with CO2 storing alternatives in new infrastructure could store as much as 16.6 plus minus 2.8 billion tons of CO2 each year, roughly 50% of the anthropogenic CO2 emissions in 2021. Massive numbers. The total storage potential is far more sensitive to the scale of materials used than the quantity of carbon stored per unit mass of materials. Moreover, the carbon storage reservoir of building materials will grow in proportion to demand for such materials, which could reduce demand for more costly and environmentally risky geological, terrestrial, and ocean storage. So carbon capture is being considered, obviously into geological storage where it can stay for a long time, and terrestrial storages into various mining operation sites, and ocean is now a big target for what we call ocean CDR, or carbon dioxide removal. So I'm going to skip a lot of the introductory material and just jump ahead. In recent years, the production of building materials has resulted in an estimated 3.5 billion to 11 billion tons of CO2 equivalent, or 10 to 23% of the global greenhouse gas emissions. Excluding energy-related emissions, the process emissions from producing the building materials we examined accounted for 1.8 gigatons of CO2 emissions in 2016, or 5% of global CO2 emissions that year. Recent studies have explored the application of emerging technologies to alter the composition and manufacturing methods of construction materials to facilitate uptake of CO2 or methane by the materials or their constituents, reversing some or most of the process emissions. So if CO2 and cement and steel production obviously contribute a lot, and we have discussed ways in which people are trying to reduce emissions from CO2 and steel manufacturing. Cement and steel manufacturing, I don't know why I'm a bit groggy today. For example, some studies have examined the potential for timber buildings to act as a global carbon sink, whereas other studies have considered the contribution of alternative cements and the impacts of concrete carbonation at end of life on the carbon uptake potential of concrete. I've discussed this elsewhere. The wildfires in LA and all the houses that went up in flames, makes you wonder about timber for building, but there are fire retardants which apparently can work and prevent such catastrophes. In this study, we examined the global potential to store carbon in some of the most common building materials: concrete, brick, asphalt, plastic, and wood. We did not examine alloys because they have very specific functional tolerances and a limited ability to store carbon. Notably, decarbonization strategies for steel may include the use of green hydrogen for direct reduced steel production. We've discussed this elsewhere. We calculated annual storage potential of building materials assuming 2016 levels of consumption, the most recent year with which for which available data the most recent year with available data for all materials, that all carbon within materials, so stoichiometric or measured, originated from the atmosphere, and that storage is effectively permanent if you do this properly. Our estimates are based on the extent to which conventional inputs could be substituted by alternatives that either contain biogenic carbon, for example, recently removed from the atmosphere through photosynthesis, or contain key materials such as recently formed carbonate materials that may solidify with the use of concentrated sources of CO2. So you're sequestering additional carbon into building materials. We assume that these building materials have negligible use phase emissions and that these materials are likely landfilled at end of life, resulting in minimal greenhouse gas emissions. However, future research could consider use phase emissions and uptake, such as the emissions associated with demolition process of building materials, which in some cases could be substantial. So most buildings are built for several, lifetime of several decades, and then they're torn down and have to be rebuilt. And when you tear them down, there is issues to consider in terms of the building materials and the emissions from destroying or deconstructing buildings. So emissions associated with burning or anaerobic decomposition of wood could also be substantial. We have highlighted companies with pilot scale demonstrations of these materials which have been claimed to have substantially lower carbon footprints and in some cases net removal of carbon from the atmosphere as compared with the use of conventional materials. So they are net negative. Further, given the uncertainty around the energy demand and GHG emissions associated with these alternative materials, we determined the total allowable emissions that would still result in achieving net carbon removal. So there are a lot of details as to how the estimates are made, but I'm going to skip all the details, just focus on the main messages. So here, carbon storage potential of alternative building materials. So we are looking at the potentials to store carbon in building materials varying considerably depending on the the carbon density of alternative materials, so kilograms of CO2 per kilogram of material, and the scale of at which conventional materials are being used as of 2016. So you are looking at carbonatable cement with the numbers. I won't go through all the numbers, but you can see, as we said already, they are substantial when you aggregate them. Carbonate based aggregates, biochar cement filler, minimum and maximum the range of sequestration. Wood, of course, you grow wood with photosynthesis, sequestering carbon and putting away the wood into buildings. Bio-based plastic, Portlandite brick. Portland cement is a way of producing cement, a clinker, the splitting of CO3 into calcium dioxide and CO2, which is a very high intensity emission process. Biomass fibers based brick and bio-based asphalt bitumen. You can look up all those things. I'm not going to go into details, but obviously there are plenty of materials which are being used for construction, and you can see global annual production of conventional materials here for each of them. So carbonatable cement, carbonate based aggregates, so you have concrete aggregate and asphalt aggregate here. Biochar cement filler, this is again global annual production of conventional material. Wood, bio-based plastic, Portlandite brick, biomass, so this is looking at global production in gigaton carbon per year. Biomass fibers fibers-based brick and bio-based asphalt bitumen. So you just get a sense that quite a large part of the emissions come from carbonate-based aggregates, which include concrete aggregate and asphalt aggregates, right? So here is a summary of the global CO2 removal potential of the materials examined based on the 2016 production values. Chemical-derived emissions for traditional materials are presented as well for reference. So you have various things here looking at global material production in gigatons, global chemical-related emissions, and global carbon dioxide storage potential into these materials. Concrete aggregate, asphalt aggregate, cement filler, brick, wood, asphalt, bitumen, plastic, and the total here in terms of material production at 32.4 gigatons, and global chemical related emissions and sequestration potential that we already mentioned, 16.6 plus minus 2.8 gigatons, which is a massive fraction of the total emissions. This is about sensitivity of the theoretical carbon storage potential for each material to carbon content and level of implementation. I won't go into the detail here, but you get a sense that as carbon content increases, you are looking at CO2 storage scale here in these colors and level of replacement. So obviously it depends on how effectively you are replacing traditional materials with these aggregates. So carbonate based aggregate, carbonatable cement, biochar as cement replacement, calcium hydroxide brick, carbonation, carbonate based asphalt aggregate, biomass fiber brick, and of course you have wood bio-based asphalt binder and bio-based plastic. I'm obviously being very brief with these things, but you get the idea that you need to be just aware of these materials and their potential to sequester carbon. Cumulative CO2 removals by 2100 as a function of the year of implementation of carbon storing technologies. Cumulative carbon storage is compared with the required targets for the IPCC targets of 1.5 degrees C in here and 2 degrees C, assuming full implementation of the technologies presented in this work. The error bars indicate the minimum and maximum values of CO2 storage. The paper goes into great details of the technologies, the barriers, which we will read a little bit in the discussion. Cumulative carbon storage by 2100 in gigaton CO2, 100% implementation of carbon storing technology will give us 1200 cumulative gigatons of CO2 by 2100. We need for 1.5 degrees C by 2025 and for 2 degrees C. So obviously you need to store away much more carbon if you want to stick to the lower target of global warming of 1.5 degrees versus 2 degrees C by 2100 with some probability like 67%. So these are first year of implementation. If you start early, you need you can put away a lot of the carbon if you implement 100% or aim for 1.5 and 2. But if you start late in 2050, then your cumulative carbon storage potential goes down quite a bit, and 2075 will reduce that even more, even with 100% implementation of carbon storing technologies. It's just a way of telling you that the earlier you start, the better off you are, of course. Assessment of resource availability constraints on the ability to meet IPCC climate change targets of 1.5 and 2. I won't go into the details again because these are always estimates based on various assumptions and the way they are modeled. Total cumulative CDR deployment necessary, minimum, medium, and max for 1.5 and 2. Need much larger storage and sequestration for 1.5 than for 2 degrees C. The takeoff year required to achieve cumulative CDR target, scenario 1 using all currently available resources, 2095 1.5, so minimum and maximum 1935. We are looking at takeoff year required to achieve, so obviously you have to go way back to reach the maximum, and this is 2090 and 2027 yeah, some details in the way these are done. Using all currently available resources but not counting increase in wood consumption, you get different takeoff year required to achieve the cumulative CDR targets. These are estimates. You can do what you want with them, but they are estimates based on scenarios, and we have discussed the scenario uncertainties elsewhere, right? Discussion: if all of the alternatives we considered were applied simultaneously, the built environment could store 13.8 to 19.3 gigatons of CO2 each year, assuming minimum and maximum carbon contents respectively. Jumping ahead, despite recent advances in industry, there are still a number of roadblocks for achieving the theoretical carbon storage uh, quantities we determined. Many of the companies mentioned remain at the prototype pilot stage of production. The barrier to large-scale production could be in part due to competitive pricing of conventional building materials and the lack of established value chains necessary for widespread implementation of these alternative technologies. So theoretically, the alternative technologies exist. They are not being manufactured and sold at large scales because traditional materials are still being gobbled up because they are very economical, and there are no compliance requirements to use these newer, more environmental friendly CO2 hiding technology. For example, carbon mineralization pathways require highly concentrated CO2 gas and feedstock rich in magnesium magnesium oxide and calcium oxide. However, CO2 sources from direct air capture are currently hindered because of high costs and so on. Okay, this carbon utilization would not offer the necessary benefits of CDR, but could provide a means to store carbon while limiting the need for geologic reserves. So if you hide it in buildings, then there are safety issues, time scale issues of how long it will stay there, and unintended consequences maybe like geological or earthquakes, seismic activities, and so on. Similarly, although biomass to polymer conversion routes have reached technological maturity, bio-based plastic manufacturers struggle to scale production because of insufficient access to biomass residues required to meet market demands for plastic. So you are going multiple steps there, producing plastics with feedstock coming from biomass, and whether they are able to scale up yet or not. So finally, given projected increases in demand for infrastructure materials, valorizing carbon in the form of long-lived materials could be an area supported through policy mechanisms, and you can argue for their urgency and so on. Strategies to store carbon in building materials are particularly relevant for policymakers because these materials are predominantly from regionally available resources, and some proposed pathways to decarbonization can drive local resource scarcities and or lead to increased health burdens on local populations. So there are pros and cons with everything we do, of course. However, they can simultaneously stimulate local economies and create jobs, and policymakers could focus on strategies to increase the use of carbon storing materials presented here with high technology readiness levels such as bio-based plastics, biomass bricks, and wood for such applications in which risks associated with the change in performance may be more limited. So obviously we'll read the second part in the next podcast, but you get this idea that there are people thinking about sequestering carbon into building materials. Building material demand is only expected to keep going up, and based on the calculations of potential for sequestration here, there could be a substantial sink or storage for CO2, and then you also have a way of reducing the pressure on doing CDR into the ocean or into geological storage systems and so on. Okay, so we'll come back and look at another perspective on building materials, which appeared in the same issue of Science in the middle of January 2025. I'm recording this just on 22nd January 2025. So sometimes I'm very up to date on what I'm recording. Sometimes I keep these articles and I do it when I get time. So I'm way behind, so the articles are older, but doesn't matter. The information is still very useful and interesting for climate solutions, climate science, climate impacts, health, etc., etc. Okay? See you in the next podcast.